Our review question for today is, what is the difference between maximum shear stress and absolute maximum shear stress? Who knows the answer to that? Yes?
Estimated to be 2 absolute maximum shear stress and 1 negative, 1 positive.
We do have 1 positive, 1 negative, same absolute value, but positive, negative. But that's not what we're referring to when we talk about this terminology. Yes?
Well, the maximum shear stress was when we did the averages for the 2 sigmas.
Okay.
Then it would be R.
Yes.
Right? And for the other one, it would be the equation where like it's A sigma A minus sigma C over 2.
Okay. Yes-ish. Yes. I'm just going to put it in some other words. Everything you said is true, but I'm going to say it differently, okay? All right, so what he's trying to say is that when we rotate an element in a particular plane and we look at the different stress components that happen on that face as we rotate it, there was an equation for R that pertained to that circle that we created, and that was our maximum shear stress in that plane of rotation. But when we recognize that we can rotate it in any of the 3 directions, when we get those 3 different circles, the largest of those circles has a radius that is our absolute maximum shear stress. So each circle has its own maximum shear stress, but we have an absolute, which is the biggest of those 3. And that mathematical equation that he mentioned, the 1/2 sigma A minus sigma C, corresponds with that. So when we have, let's say we have our Mohr circles, and let's say they look like this. Sigma A is going to be the biggest of these principal stresses. Sigma B will be the middle, and sigma C will be the smallest. So that corresponds to those 3 values. So if you calculate 1/2 sigma A minus sigma C, that always gives you the radius of this biggest circle. All right, so this here is our absolute, and then R for a particular circle is that one. Good. So I wanted to bring this up as our review question today because today's topic is initial yield and failure theories. And it relies extensively on an understanding of shear stress. And in particular, we'll talk about maximum shear stress.
So it was like confined loading, like kind of like really like short thing.
Kind of. Yeah, because, so the question is, was combined loading a real short topic? We had a lot to learn to understand axial loading and torsion, a little bit to understand pressure vessels. There was nothing particularly new in combined loading. It was just taking 2 of those scenarios and putting them together and then showing you that you could superimpose those stresses. So yes, it was fairly short. We will come back to that topic later when we cover beams. We'll then incorporate bending into the combination. So this topic is not a continuation of what we've been doing. This is kind of an entirely different topic. This is very similar to what we did in the beginning. And in fact, in some semesters I've taught this in the beginning, but this semester I kind of eased off and moved it a little bit later in the semester. This topic is something that you will definitely see again if you're going mechanical engineering. In your next class, you will cover this again in more depth. But I want to introduce everyone to it here so that for mechanicals, it's not the first time you've seen it when it comes up in your next class, and for civils, you've at least seen it. Because if you go to grad school, people will start talking about these things, and if you don't know what they're talking about, you just look like that kid who doesn't know what they're talking about, right? So you at least want to be able to play along and say, oh, yeah, I know von Mises, And then you go back and you look it up again, okay? But you don't want to be blindsided when they start throwing these terms out. So when we talk about yielding, let's first kind of remember what yielding is. Yielding refers to large deformations with relatively small increases in applied load. So when we were dealing with uniaxial materials and we plotted our stress versus strain, our curve might have looked something like this, where in the beginning we had large increases of stress for little increases of strain, and in fact, the true slope should be much steeper than what I've drawn there. And then you get into what we call the yielding region. So that would be this region over here. And now you start having very large increases in deformation, but only small increases in load capacity. And this yielding is caused by the slippage of the molecules along oblique surfaces due to shear stress. So it's kind of a mouthful, but the idea is that in your material you have all these molecules arranged however they're arranged, and you end up having, by oblique surfaces, I mean kind of along this plane, they start sliding past each other. And that causes yielding. Once yielding occurs, Hooke's law no longer applies. Right? We know that it's only in the elastic region where we can use this linear relationship between stress and strain. And for engineers, we typically consider yielding failure. Typically, we're not designing things to behave ductily in this plastic region. There are a few exceptions. So for example, for earthquake engineering, structural engineering, we do design portions of buildings to perform plastically, and we call that a fuse. So we expect that area to deform and elongate during an earthquake, allowing everything else to remain elastic and undamaged, and then we can come back in and just not retrofit, but repair that one particular fuse region. So we do utilize it, but by and large, we want things to remain elastic. So it's really important that we know when something is going to fail. In the uniaxial stress state, it was fairly simple. We only had one non-zero normal stress, right? Our two transverse stresses were zero. We had one longitudinal stress. And so we said, well, when that stress value equals our yield stress, sigma capital Y, we must yield. It was pretty straightforward. And we determined this value of sigma Y either from the lower yield point on our curve or from the 0.2% offset method. Now what's kind of interesting is even though throughout your career you're going to hear over and over again that when the normal stress exceeds the yield stress, it yields, referring to uniaxial material, it's actually not the yield stress that governs at all. It's really the shear stress that governs whether or not it's yielding. Because that goes back to the definition of what yielding is. It's slippage along that oblique surface. And so it's really the shear stress that governs. But it also coincides with this normal stress being equal to sigma Y. But that's not really the driver. So what we're going to see today is two different methods of explaining when something yields for a multi-axial stress state. Because it's fairly simple for uniaxial. You had that down in like month 1. But now that we have pressure vessels, we have stresses, normal stresses in two orthogonal directions. And I would argue that when either one of those reaches yield stress, you're definitely going to be yielding. But there's going to be some combination of stresses in those two orthogonal directions where neither one reaches this yield stress, but yet your material will yield because of that combination of the two. And we're going to look at how we quantify when that happens. Any questions before we do that? All right. So the first method is called the Tresca yield criterion. And in quotes here, I have written the concept that explains all the functions. So this first sentence is what we're trying to achieve. A material under multi-axial stress state, so for example, that could be our pressure vessel, the more than one normal stress, will yield when its maximum shear stress reaches the value of maximum shear stress that occurs in a uniaxially loaded material at yield. So essentially what this is saying is that there's some shear stress that causes failure of a material. Whether or not you are in uniaxial or multi-axial, it's the same shear stress that it's going to fail at. And we know that it yields at normal yield stress, so we're going to figure out what's the corresponding shear stress, and then when we reach that, we expect our material to yield. So remember our kind of review question at the beginning was, what is the formula for the maximum shear stress and the absolute maximum? This quote doesn't say absolute, but it intends absolute. So this right here is an absolute value, absolute maximum shear stress. It's 1/2 sigma A minus sigma C. So essentially that's the radius of that biggest circle. And so let's take a look at what that looks like for uniaxial stress. What does your Mohr circle look like for uniaxial stress? Okay. And what are the two normal stress? What are the two principal stresses? Yes, you're being so general, but you are absolutely correct. Yeah, we have sigma average is the center, sigma 1 and sigma 2 are our principal stresses. For uniaxial, I would argue that P over A is going to be sigma 1 and 0 is going to be sigma 2. So you're going to get this circle. Now, if you're yielding, P over A becomes sigma Y, your yield stress. Now, your other two circles, one will be identical to this and one will be a dot at 0. So from this, you know that your maximum shear stress is this radius. What's the magnitude of that radius? Yeah? Yes. I have a diameter that's equal to sigma y, so my radius is good. So sigma y over 2 is the radius or the shear stress that occurs when we have yielding in a uniaxial material. Is there anybody who objects to that or who has discomfort about that? We're all on this same page? Oh, it's on the PowerPoint. We're all on the PowerPoint slide. Okay. Excellent. So when we have uniaxial loading, the shear stress that occurs at failure is magnitude of sigma y over 2. Sigma y being a material property of that material. So this is a constant value. Therefore, when our absolute maximum shear stress equals the magnitude of sigma y over 2 for any loading, we say it's yielded. So that means that so this is what our equation looks like. We can multiply both sides by 2 and it reduces to this. Or if you want to write it in the more general term, you can write it like that. Okay. But the point is, for any multi-axial loading, we need to figure out what our sigma A and sigma C are. Then we can figure out our absolute maximum stress, and then we can see how that compares to our yield stress. So let's do an example to illustrate this. We're going to look at a strain rosette that we've attached to the fuselage of an F-35 airplane. And down at Edwards Air Force Base, they're testing these. They're going to read the data from the strain rosette and be able to tell how this material is performing, what the stresses, what the strains were, and then what the stresses were, and ultimately how close is it to yielding. So if you have a strain rosette, remember that's 3 strain gauges attached like so, where this would be strain A, strain B, and strain C. We have our material properties, Poisson ratio, modulus elasticity, and yield stress. We want to first determine, has the fuselage yielded? If not, how close are we to yielding, right? We currently have a 3 psi pressure differential between the inside and the outside of the airplane. What would this pressure differential have to be in order for it to yield? How might we approach that problem? Now, there's 1 of 2 ways to figure this out. You can either start with what we know and work towards what we're trying to find, or start with what we're trying to find and work your procedure back to what you know. What's your preference? All right, so what do we know? What's given in this problem? Yes, we have strain values. Strain A, strain B, strain C. Okay, and material properties. What can we do with those? With strain values from the strain rosette and material properties? When you say actual strains, what do you mean? Okay. Oh, did you say axial? Actual. Okay. Yeah, so we can get these onto some coordinate system, X, Y, and Z. Okay, and get our shear strain, because first we had 3 normal strains. We want 2 normal strains and a shear strain. Okay, so now we have our strain state. What can we do with our strain state? Okay, so we can get sigma X, sigma Y, and then shear stress, tau XY. Good. Once we have those, these are just an arbitrary stress state. To get, okay, sigma A, sigma B, sigma C, right. So we can get our principal stresses. And we'll probably get R, not that we need it, but we'll, okay. Once we have those, then we can get our maximum shear stress. Okay, cool. And we'll compare that. We'll check whether it is less than or equal to the yield stress over 2. Good, we have a plan, a very solid plan. So we start off with the sigma A, strain A, strain B, strain C. Strain A is the same as, we'll say, strain X. Strain C is the same as strain Y. So what we really need to find is gamma XY. And who remembers the equation to do that?
It's 2 times strain B minus strain A minus B.
Good. We have 2 times 822 times 10 to the negative 6 minus 1262 times 10 to the negative 6 minus 758 times 10 to the negative 6. So that gives us a strain of negative 376 times 10 to the negative 6. And that's going to be inch per inch. Now we're going to use G, right? Because now we want to calculate, our next step is to calculate tau, or shear stress. That's G times gamma. G, we weren't given G, but we can compute it. It's E over 2 times 1 plus Poisson ratio. And we're going to multiply that times gamma xy. And if we do that, we get negative 1468 psi.
68 radius.
68. Thank you. Okay, then we calculate sigma x. And the equation for that is E over 1 minus Poisson squared times the strain in the x plus Poisson times the strain in the y. That equals 15,997 psi. For the y normal stress, we have a very similar equation, except now it's the strain in the y plus Poisson times strain in the x. So we're going to get 12,059. So now the fact that we have two non-zero normal stresses, we know that this gives us a multi-axial stress state. Right? So this is not uniaxial.
Are those commas or decimals?
Commas. So that's 15,997 and 12,059. The next step is calculating our radius, our R value, and our principal stresses. So R is given as the square root of sigma x minus sigma y over 2 quantity squared plus tau xy quantity squared. This is 2456 psi. Now sigma 1 and sigma 2 are sigma average plus or minus r. So we have sigma x plus sigma y over 2 plus r. So it's approximately 14,000 plus this 2456. It's going to give us a value of 16,484 psi. And sigma 2 is, of course, sigma average minus r. And so that's approximately the 14 minus the 24. So I give this 11,572 psi.
What are these two equations? The same old ones that we used?
These are from the beginning of the semester, fought a long time ago. R is, we derived it algebraically, but turns out it's just the radius of that circle.
Just the sigma 1 and sigma 2.
Mm-hmm.
These are the same two ones that we used?
Mm-hmm. Yeah, the average value plus or minus the radius. Mm-hmm. Okay, so now we want to line those up with sigma A, which is bigger than sigma B, which is bigger than sigma C. So our third stress, our third principal stress is 0, right? Okay. Now we're assuming that because there may, if we actually calculated it, maybe there'd be some small value, but we're assuming this fuselage to be plane stress. It's a very thin material, so we're going to neglect whatever small stress there may be numerically in that other direction. So then we're going to map these three stresses to A, B, C. The largest one has to be sigma A. The smallest one has to be sigma C. And the medium one has to be sigma B. Which means if we're calculating our absolute maximum shear stress. So tau absolute max, 1/2 sigma A minus sigma C. That is 1/2 times the 16,484 minus 0, which is 8,242. So this is the absolute maximum shear stress that our material is experiencing. But we want to compare that yield stress over 2, because that's the shear stress at which uniaxial would yield. So 64,000 was given in the problem. So 32,000 would be the sigma y over 2. So have we yielded? No, we're less than 32. In fact, we can calculate a factor of safety, which would be 32,000 over 8242. And that gives us 3.8. So we could increase our pressure by 3.8 times before we would expect to see yielding. Which means if our pressure is currently at 3, did I say KSI, PSI? What is it? PSI. We're at a 3 PSI differential right now. 3 times 3.8 larger, we could take it all the way up to 11.65 PSI before I would expect yielding. Okay, yeah, question.
How did you know it was that case to have the sigma absolute max? Like it was the sigma A minus sigma C?
Because that is the general equation. It's always that case. Because sigma A is always your largest, sigma C is always your smallest principal stress. So therefore, this equation always gives you the radius of the biggest circle. The other options are you can choose between R sigma 1 over 2 or sigma 2 over 2, and those give you the 3 different options, and then you pick the biggest one. But I like this way because this always works.
Okay.
Yeah. Other questions?
And sigma y was the lower sigma that we got, right?
Capital Y?
Yeah.
Sigma, that's our yield stress. That was given in this problem.
Oh.
Other questions? Okay, cool. So that's Tresca. But there's also von Mises. These are 2 different theories. They're 2 different theories that aim at doing the same thing. They're both aiming at predicting whether or not you're going to yield. Yes?
Does it just matter what type of values you have? Or could you use, could you have the same givens and use the same theory, 2 same theories?
You mean the 2 different theories? Yes. Yeah. So they're just independently 2 different people made 2 different hypotheses. And at the end, I'm going to show you how these 2 relate, whether in terms of your results. Okay, so this one is a little bit more difficult to understand the concept. So just try to pay close attention. You may want to go back over this later. When we have uniaxial stress, we just have one normal stress that is non-zero. The other 2 are 0. So when we're talking about uniaxial stress and we talk about work being done, the general equation for work is always 1/2 force times distance. Okay, so you take your normal stress, you multiply it by an area, that gives you a force. Then you multiply by the strain times that length, and that gives you a distance that you're acting over. That work equation that I give you there is for uniaxial stress in the x direction. And that ends up equaling 1/2 stress strain times volume. Earlier in this class, we talked about strain energy density, which was work per unit volume. And that was the area under the stress strain curve. So here you can see that the relationship between work that you talk about in physics, which is a force times a displacement or a force integrated over a displacement, that ends up having a volume in it. And so if you divide by that volume, you get what we call strain energy density, which is the area under the elastic portion of your curve, your stress strain curve. Now, if we want to look at multi-axial stress, you have this happening in each direction. So now you have 3 different terms, each of which is creating work. If I want to get this entirely in terms of stress and take my little strain variables out, I can represent each strain by the generalized Hooke's law, where strain is a function of stress. I then plug that into this equation, and I get an equation for U, which is our strain energy density, that work per unit volume, that is entirely a function of stress. And these happen to be principal stresses because we are only applying normal stresses on this object. We're not applying any shear stresses in this scenario that we're talking about right here. Now this strain, in general, strain energy consists of 2 different components. One is what we call hydrostatic energy, which is the energy that is in the body due to the change in volume. So when we apply equal stress to all 3 sides, we get change in volume and no change in relative dimensions. And so that would be our hydrostatic energy. The rest of the energy comes from the distortion of this volume. So elongating in one direction relative to the other. And that's what we call our distortion energy. Now, interestingly enough, yielding is entirely or is only dependent on the distortion energy. If you were to deform an object entirely with hydrostatic energy, so equal suction, say, on each side, you would never yield that material. You have to have the distortion or the elongation of one side relative to the other to cause yielding, which should not be entirely surprising once you internalize what I said earlier about yielding really being governed by shear stress. You don't get shear stress if you're equally expanding all of the dimensions. So in words, what this theory says is that a material under multi-axial stress will yield when the maximum distortion energy per unit volume, so that's this UD thing, when that reaches the value that it reaches when a uniaxially loaded specimen yields. So I'm saying there's something called distortion energy per unit volume. You can calculate it with uniaxial loading. Whatever value that is, when you reach that value for other types of loading, you're going to yield. That's what this theory says. So we can look at that equation that we had earlier. So remember this equation for U with all these sigma 1, 2s, and 3s. Let's go ahead and plug in these distortion stresses, which are each of the 3 stress directions minus the average stress. So if you take the total stress state, which is sigma 1, 2, and 3, and you subtract from each of them this average stress, which we say is our hydrostatic portion, what's left are these deviatoric stresses. It's how much the stress applied is minus the average value. So if we plug that in for the values of sigma 1, 2, and 3 in that equation, and then remember that the average value is the sum of the 3 divided by 3, you end up with this equation here. So this then becomes our deviatoric, is that right? Let me see. I take it back. This is the general equation. This is the general equation. When we plug it all in, we get our deviatoric portion. Your question?
What is that?
It's the portion that is not symmetric. It's the portion that is beyond the application of your sigma average in all directions. So if you apply sigma 1, 2, and 3, let's say you apply 5, 10, and 5, 10, and 15 KSI to this object, okay? That's the loading that you have. The average of those is 10. So I can say that each of these consists of two different components. This is 10 plus 0. This is 5 plus, let's keep it consistent. This is 10 plus 5. And this is negative, what am I doing? This is 10 minus 5. Okay, would you agree that in that case, all of those add up to what they originally were? So in all cases, I'm adding a 10. And then I'm also adding a negative 5, a 0, and a positive 5. And that gives me my 5, 10, 15. So this here is like the 10, 10, 10. And this is the remainder. This is the negative 5, 0, and 5. This deviatoric portion is the portion that makes it change shape.
So it's the difference between the y and the average? Yes.
Yes. Now, if we want to be a little bit more technical, so you said it's the difference between the applied stresses and the average stresses. That's true. Those average stresses have a very special name called hydrostatic pressure. It's where everything has the same stress on it. Every face has normal stress of the same magnitude. So this is the general equation that we started with. When we plugged in our deviatoric stresses, which for this example would be the negative 5, 0, and 5, but mind you, they're written as sigma 1 minus average, sigma 2 minus average, and sigma 3 minus average. When we put those into this equation, and remember that sigma average can be written with this equation here, where we sum all the components and divide by 3, what you get is this equation, and that represents our deviatoric strain per unit volume. Strain. Okay, so in plane stress, one of these components is 0. In plane stress, we say that sigma 3 is 0. So it further simplifies to this equation here. That's what you're going to get if you plug in sigma 3 equals 0. And then do the algebra to simplify the mathematical equation. For uniaxial stress, it reduces even further. Right, for uniaxial stress, you just have one stress. So you'd have your sigma 1s. Sigma 2 would be 0. So all you have is this term here. And you put in your stress value, sigma y. So take a second, absorb that. For uniaxial, this is your deviatoric stress. And that's going to be some number, because sigma y, Poisson, and E, those are all constants. Then we're only going to be looking at this in this class in terms of plane stress. So that has to be equal to this value. Which means you can cross off this or cancel out this constant term, because it's going to be the same in both. Now if you take the square root of what's left up here, you get this, and that has to be less than or equal to our yield stress. So that's the statement for von Mises. This line here is what I want you to remember. The rest of that derivation, I just want you to understand that this equation comes from equating deviatoric strain energy per unit volume. Okay, you don't need to be able to reproduce that derivative or that derivation. Just understand we're dealing with strain energy, deviatoric strain energy per unit volume, and this is the equation you get for that. So we can apply this to that same example with the fuselage. At some point in our Tresca analysis, we ended up, I think that is mistyped. We ended up here, but this should be 16, right? Okay, so up to this point, the procedure is the same. But now that we have this, we're going to take the square root of sigma 1 squared minus sigma 1 sigma 2 plus sigma 2 squared. So this is the square root of 16,484 squared minus 16,484 times 11,572 plus 11,572 squared.
So sigma 3 is always 0, right? Okay.
When we're dealing with plane stress, sigma 3 is always 0. And in this class, when we deal with von Mises, we will only do it with plane stress. Out there in the real world, you may come across a 3D stress state with 3 components. And then you, instead of comparing it to this equation, you would then, so if you're in the 3D world with all 3 stress components, you would compare this same equation for uniaxial, but you would compare it to this equation here.
So you get a 1/2.
Yeah, they're right, because this is off by a factor of 1/2, so you'd have a 1/2, and then you'd have square root of the rest of that. Yeah. Okay, so here, I believe this gives us 14,659. Did anybody calculate it? Okay, is that right? Okay, so if we do that math, we get 16,659. We compare that to sigma y, the yield stress, which was 64,000, and we say, nope, we haven't yielded. But what's interesting is to look at our factor of safety. 64,000 divided by 14,659. And what do you get for that? Okay, 4.4. Before, didn't we get 3.8? Now we get 4.4. So I'm going to draw you an image to illustrate this in just a second. But essentially, the Tresca is always conservative, except for when they're equal. There are times when the two give you the same answer. But other than that, Tresca will always predict yield to occur sooner than the von Mises predicts it. So to put that into a graphic, the way I would do that is I would plot sigma 1 and sigma 2. And there are some key points on this graph. For example, when sigma 1 is equal to the yield stress, or when sigma 2 is equal to the yield stress, oops, or when they're equal to the negative of the yield stress. So those are really important points. And on the Tresca, we say, oops, we say that if we're on this hexagonal, it's not exactly hexagon, but elongated hexagon shape, we will be yielding. So essentially when sigma 1 is equal to sigma y, when sigma 2 is equal to sigma y, all the way up to when they're both equal to sigma y. Same thing down here if you end up with a negative sigma y. And then when you have anywhere on this curve where the two are kind of summing to whatever, or not summing, but when the two components land you on that diagonal, you'll also yield. So that's your yield surface. If you are anywhere inside of that, so if you plot sigma 1 and sigma 2 and you're inside of that, you have not yielded. You're behaving elastically. If you get on this surface, you are yielding. You can never get outside of this surface because it's kind of like when you're surfing in the ocean, right? Now I don't surf, so I'm gonna mess this metaphor up completely. But the point is, you and the wave move together, right? More or less, that's the idea of surfing. With my limited knowledge, that's my understanding of surfing. I want to be on my surfboard, I want to move with this wave. So you can think of the wave, you are the specimen, and you're on this wave. You can never get like beyond that wave, because as you're moving, as you're yielding, your wave is moving, which represents the fact that your yield surface is getting bigger. And so you can go back to thinking about stress and strain. So remember we talked about, this is, say, our stress strain curve. And if we're in the elastic region, we move up and down, right? This is our loading, unloading. We go up and down that curve. But then when we come out over here, we yield at this point, and now we move over here. Now if I unload like this, parallel to that initial curve. And then if I reload, I go up this curve. So now I can bounce back and forth on this new kind of elastic region. But you'll notice that you keep being elastic past your previous yield stress. Now that you're on this blue curve here, you stay elastic until you come back to that point where you left your initial stress strain curve. And so what that means is your yield surface has expanded from here to there. That makes sense? Okay, so this is Tresca. A little bit easier to understand, but it gives us conservative values. Now, von Mises will give you the same values when you are at any one of these vertices. So at 6 particular points, you'll get the same result predicting yielding from von Mises. But von Mises, if you look back at that equation, this equation here should look somewhat familiar to you from calculus. The sigma 1 squared minus sigma 1, sigma 2 plus sigma 2 squared. Well, what it gives you is an ellipse. Okay. So you end up with an ellipse here. And so you can see that you're going to have, so this is, let me see, you're going to have a discrepancy anytime you get away from one of those 6 vertices. And the biggest difference, is here. And it's about a 15% difference. Now the von Mises is more accurate. So if you're doing it by hand and for whatever reason you think Tresca is going to be easier for you to do, that's fine. Just know that you're being slightly conservative. If you are analyzing something using computer software and you're looking at stresses, and I would argue that in that case, if it's just a click of a button to compare Tresca versus von Mises, there's no reason not to compare von Mises, right? If someone else is doing the math for you, if the computer is crunching the numbers for you, why not choose the more accurate analysis method? So von Mises is the preferred method typically for analysis, but Tresca does exist, and if you feel like it's easier and you're just doing a back of the envelope calculation just to check real quick if something is going to work, you can do Tresca. Cool? All right, let's give it a try. So we're going to look at an element. And that element has stress components of positive 50 KSI. No, I take it back. 50 KSI is the yield stress. It has positive 12 KSI, negative 8 KSI, and then positive 7 KSI for the shear stress. So using both methods, figure out what the factor of safety against yielding is.